Hello everyone, welcome to lecture on formal specification and verification using Coq proof assistant or Coq theorem prover. In this lecture I will continue formally specifying different simple systems, defining data types and then defining some functions over those data types and then proving some simple lemmas and theorems. To understand the basic concepts of functional programming. In this lecture, I'll mainly focus on polymorphic definitions or polymorphism, which is a very strong feature of the Coq proof assistant. And this polymorphism, parametric or polymorphic data types are defined in functions that take other functions as argument are defined. This is the most strong feature of functional programming languages like Coq. So far we have defined libraries, induction, basics, and these two libraries were compiled and then included in less.v, and we completed and wrote a number of definitions and lemmas and until we ended this library, and this library can be compiled till the end. So now this library is complete, and now I'm going to open a new file and save this with fully. Let me save this with polymorphism. So I will just save it fully.v, and as this library is already there, so I'll just rename. I'll replace that library with our new library. This library is currently empty; it has nothing, and this library corresponds to the chapter 4 of the Software Foundation book, and also the definitions are similar to the one that have been described or written in the book, so that it is easy for you to follow. I will use require, import, and list.v because that would be needed here. So after list, so when I compile this, list.v is accepted, and the reason is that we have already compiled using the Coq compiler, Coq-C compiler. So I have compiled this list.v, and now it is accepting that. So by requiring this list.v or the compiled version of that list.v, which is just mentioned as list. So all the definition and theorems and lemmas are imported here, so we can then use them. Okay, so in list.v file, we defined list. So we defined list of natural numbers, and we called that list of natural number as list of net list. Let me just show you that definition, and we had that definition somewhere here. So we defined this definition, and it is a list with two constructors, null and cons, and it has an argument n of type net and a list of net list type. So this is the initial, the base. This is we call null a list, and then anything of type list and a natural number with preceded with cons constructor. This also becomes a list, and this way, using these two constructors, we were able to create elements of net list. So net list is a list, as the name indicates. It's a list of natural numbers. But here in the polymorphism or polymorphic types, if we, for example, if we need to define another list of Boolean numbers, list of bool data type, or list of strings, or lists of lists, or any other list. For example, we can start to define inductively. We can define list of bool or bool list, So that would be defined like bool list, just like netlist, and it is a type, sort type, and it is defined as with two constructor, and one is bool null. It is just to differentiate it from the null used in the netlist type, and bool null. So this is the null list, and bool cons. And this constructor is taking a boolean value of type bool, and a list. It is taking a list of type bool list, and this is to be defined as a list. So this is a bool list. So it is a list of elements with every element has a type bool, just like we had a list of natural numbers where every element had a type nat. So it was list of natural number, and this is a list of bool values. If we continue this, like to define a list of strings, a list of lists, for every list we would need constructors like these two. And as we had null and cons used for netlist, we used bool null, bool cons, and if we are defining a list for string, then we would use string null, string cons, and if we are using lists of list, then you would use null null or list null or list cons, and so on and so forth. So this is a bit awkward because we are using two constructors for every list, and we cannot we must have different names for every constructor and function name. So eventually we will have shortage of names, proper names, and apart from this, we need to define all the functions for every list. For example, for netlist we had function to reverse length, and similarly searching the list for a natural number. So and number of lemmas and theorems, we had a huge script or meta theory for list in the lists.v library. So if we have, for example, if we continue with this way, we would need to define a list for every type separately. We need to uniquely name the list as the list type, or as well as the constructors. And also we need to define all those functions again and again for every list of different type. And also we need to develop that theory again and again, defining lemmas and theorems. For example, if we need to define the convolution or involution theorem or commutative theorem, then we need to define it for the new list as well. So there would be a lot of redundancy, and this is not a good practice. But luckily, Coq allows to define polymorphic inductive data types. So different types, inductive types, can be defined in a polymorphic way. And by polymorphic, we mean that they are parametric by data type. So a data type is generalized data type is or type variable is used as an argument, and the specific data type is not mentioned. And doing this allows us to define one list but reuse that list for every other data type. And also we would not need to name this list separately. We can just reuse it, and also we do not need to define or to use separate constructors. We would be able to use the same constructors, the same list name for every data type, and also the same theory, the same lemmas and functions would be reused. So let me start with a list, and this list is polymorphic inductive type. So I continue with the same inductive keyword, and we just call it list. And the only argument of this list is a variable. This is called a type variable of some type, sort type. And this is a type just like the bool list or net list. So these lists had no argument, but this list, which is a polymorphic list or polymorphic data type, has a type, and that is the only one argument, and that is x type of sort type. So this is a type variable. This x represent a type, and whenever a type variable is used, normally the convention is that the type variable is normally in uppercase. Okay, so this is to be defined as it has two constructors, and one constructor is just null, and the other constructor is cons, and this constructor will always have a variable x of type x, and this will have a list of type list x, list of the same data type as is provided in the argument. So this is a parametric or polymorphic type list. Let me compile this so this is acceptable. So what this list is doing, this is a list of elements of type x. Now x is unknown, x is a type variable, so any data type like natural number, bool, or string, or any data type can be passed as the argument, and a list of that type is then defined. But the whole process of defining this polymorphic list is similar to the other list, bool list and net list. We have constructor null, we have constructor cons, we have an element x of this data type, and we have a list of this data type. And the only thing that we had to provide when we are defining a list of any other data type is to provide a data type, and that data type will be passed as argument to this x, and this will be the variable, the type variable will be replaced with that data type fast. So we will see some examples shortly. So this is a polymorphic definition of list. We can check the type of this list. We can use the check command, check list. So we will get the data type of this list. So in other words, this list is a function from type to type. We can say that it gets a type and it returns a type. Or it can be said that list is a list of elements of type x data type, where x is a type variable. It can be any data type. One more thing about these constructors, that we had included the constructors. We had used the same constructor null and cons for the net list, but we had included all those definitions in a module. So as those definitions and lemmas were included in a module, we do not face a naming error, a syntax error that this name has already been defined, because they are out of scope, because they are inside the module, so they are out of scope. So whenever we want to use some definitions or names or lemmas, and we want them to not create naming issues later on, we can include them in a module, so they are then out of scope. So here those definitions of net list are out of scope here, even though we have included list.v, but they are inside the module, so they are out of the scope here, and so that's why it's not giving a conflict. Okay, we can check the constructor null. If we check the constructor null, it would complain. It should complain, I think. Okay, so it is not complaining, but it is defining the constructor null for all type variable x, and it says that null is a list of type x. So x is a type, and if we provide null, we use null. Null is a constructor, and we provide net. Then that x would be replaced automatically with data type net. So now this null net is a list of net, so it's a null list, but it's a list of type net. Similarly, we can check the constructor cons constructor, check cons, and we can use net, data type cons net. So every time we are referencing these this function or this constructor, we must provide a value for the type variable x, or otherwise if we do not provide the name or the value for the type variable x, then it will replace it with for all x. So if we are reusing this list for a particular data type, then we can use the data type as the argument. So null net would define null as a list of net. Similarly, cons net and other elements would make a list of net data type. So for example, cons net, and we provide 3, and 3 is one element of the list, and then we provide null, which is which ended this list, which ends this list. So this is a list where we define 3 is the only element in this list. So when I compile this, okay, so this list is defined as a list of net because net is the data type, and this list has only one element, and that is 3. Remember that we are not using the notations. Notations are also inside the module. So we would define the notation shortly for this polymorphic list. Okay, so these are some examples of how we can trigger, or how can we refer to these constructors, and we will see some other examples of the list as well. So okay, so this pattern is very good for list, and we can now define some functions that were defined for the net list, or also some new functions that would be working on this new data type. So let me define a repeat function that is repeating a value as many times as desired. So it is actually, repeat function is creating a list of data type x with the number of occurrences, and the value to be repeated is passed as the argument. For example, we had a similar function. Let me see if we had a function repeat here. Okay, so we had this function repeat. This repeat function is getting two natural numbers n and a count. So this natural number n is repeated as many times as the value of the count, and it returns a net list. So it is repeating the number n that is passed as arguments. For example, repeat 2, 2 is repeated 3 times in the list. So 2, 2, 2 is the return net list. So quite similarly, we are using a repeat function that is generic, that is not only accepting natural numbers, but any other value of any other value of any other type. The count, of course, value should be of type net, because that is a natural number, and that represents the number of occurrences of the value to be repeated. So let me define this function, fixed point repeat, and as usual, it should have a type variable as argument. So this is type variable x, and this would be referenced or given. This would be given a type value when this repeat function is used for a specific type. So this is a type. The first argument is the type variable, and then a value of this data type that would be repeated as many times as the value of count, which is a type, which is a value of data type net, and this would return a list of data type x. And this function is defined as, so we use pattern matching, and pattern matching on the count, which is a natural number, and it has two forms or two constructors. One is if it is 0, and if it is 0, then a null is returned. The list is empty because the number of repeating this value x, is 0. So 0 times this x is repeated, that means empty list, and this would be written as null, but x should be used because this is the type of this list as we used here. So whatever the data type is provided as the first argument, that would be a return here. So if, for example, it is net, then this will return nil net, or if it is bool, this will return nil bool. And similarly for the other case, when the count is not 0 and it is successor followed by some count prime, then what it should return? It should return that appending this x at the head, making the first element of the nest. So that is created using cons. And the first argument is the same data type variable x, and then the value x, and this is appended at head with a repeat. X is again the same argument, the type variable, the value to be repeated, and the count prime, which is one less than the original value in the first iteration, and this is ended with dot. Okay, so when a count is 0, so it will return null x of the same type. When it is of the type s count prime, when count is not 0, then it will first create an element cons x. So this x is the first element at the head of the list, and then for the rest of count prime, this repeat function is again called. So let me compile this function. It is accepted. Okay, so this is repeat function, and now we can compute this repeat function. For example, using compute function repeat, and we can repeat net is the data type, that is the first argument, and net is the first argument, and then we pass a value of this net data type, that is 4, for example, and we want to repeat this 4 5 times, and we want to create a list of data type net where 4 is repeated 5 times. Let me compile this. So 4 is repeated 5 times. 1, 2, 3, 4, and 5. This would we are using repeat function, which is defined for the type variable x, and but we are using it as for net data type, and we are providing the values here. This value will always be of net data type because it is fixed here, because it represents the number of repetitions. So the number of repetition is a natural number. But here this argument, this value that is to be repeated in the list can be different. If it is a net, then it is a net. And for example, we can use the same compute function, compute repeat, and for example, we can pass bool data type, and we can repeat true 5 times. Let me compile this. Okay, so this function, this computation passes the data type is bool, and the value that is to be repeated is true, and the number of times that this true should be repeated is 5, which is a natural number. So 1, 2, 3, 4, and 5. This one was missed. So okay, so we can use the repeat function even though this repeat function is defined once, and this is defined as a parametric or polymorphic data function, which takes a type variable here as the argument, and then the rest of the body is defined for that specific data type. And this is independent of the data type, so any type can be passed here, any data type can be passed here, and this value can be of any data type. For example, for the net and bool we just saw. So this is the beauty of polymorphic data types and polymorphic functions. We do not need to define this repeat for once for net, and then again for the bool, and then again for the list, or again for any other data type. So we can just define any other data type, and we can use these lists, and also this repeat function can be used for any data type. So repeat function is common for all data types and for all lists of any data type. So we can now define any lemmas and theorems for the same function, and we can continue with this. Okay, so here we are using in this type of definition, we are giving the types of variable. For example, this type variable has the data type, and this x is a variable of a value of this data type, and we are also passing the type of count. we can define this function without mentioning the data types in the argument here, like we had the types type, x, and net here. So we can skip them. Let me use this variant of the function. I call this repeat prime, and we are just passing one argument which is x, another argument which is x, small lowercase x, and another argument count, and we just return list of x, and this is to be defined as, okay, so match count with, sorry, there is no vertical line here, but we have line here. Okay, so when the pattern of count resembles 0, then it should return null x, and when it is similar to some successor followed by count prime, then it should return cons x, lowercase x, just like the function we had defined here. So repeat prime, just the name is different, x, lowercase x, count prime, and it is ended with n dot. Okay, so this is the same function, but we are skipping the types of variables here. And let me compile this if it is happy with that. Repeat. Okay, so repeat is not here. The reference repeat was not found here. Why is this giving this error? It should not give an error. It is giving an error, and okay, sorry, we have a typo here. We have missed the equal sign. Be careful with these typo errors, because the Coq is totally unforgiving. It's not forgiving anything, so be careful. Okay, so what happened here is actually we did not mention the types of these variables. So what is happening here? We are pattern matching on the count. So the count patterns, one is 0 and the other is successor followed by something. So it automatically Coq infers the type of this variable to be natural number. So it is a type of natural number, and as we are using null here and we are using x here. So null is a constructor of less data type, and less data type, what null follows is the type variable x. So x is a type variable, and automatically it assigns a data type type to it. And similarly, cons x, where cons has the first argument is the type variable x, and the second argument is the value of data type x. So x is assigned the data type x, and so all the types are inferred automatically by the Coq compiler. So this is a good thing. In any case where type inference can be used, it is good to use this feature, but remember that when the types of these variables are skipped, sometimes it is difficult for the user to interpret, so it's better to use them for documentation purposes, and also for understanding later on by other readers or by the same developer. Okay, so this let me check the type of these repeat. What is the type of this repeat? So it's repeat has the type for all x of a sort type. It has the first argument type variable, a value of the natural number, and it returns list of x. So it's the count, and it's a type variable, and it returns list of x. And if we check repeat prime, then it is the same data type. The same type is used for the function. It's just the name is different. Okay, so in this function, we are using this variable type variable every time, and this is sometime a bit boring. So Coq allows us to skip this style of definition, and instead this can be replaced with a space holder, which is an underscore, and this that underscore is filled by the Coq itself. So let me use that style. Text find repeat double prime, because we have used repeat without prime and repeat single prime, and we use the same style as above, x count, and it returns a list of type x, and it is to be defined as, okay, so match count with, when the value of the count is 0, it returns null, and it was followed by a type variable x, but we want to skip this, and we ask the Coq compiler to fill this gap, fill this place by a type, and as the type argument is x, so it will automatically fill this with the data type x. Similarly, we can continue with the non-zero case, successor followed by something, and this is cons, and here we had a type variable, but now this is replaced with an underscore, and the value that is x to be repeated, and repeat, it's a recursive call, and again the type variable that is x, it is again replaced with the space holder, and x count prime. So everywhere we had in the constructor we had a type variable x, we just replaced that x with the space holder, and this space holder is the underscore. So what happens is that Coq compiler automatically fills these space holders, and we can again check the type of repeat function, and that would give us the same data type which we had for the repeat and repeat prime. Okay, so we can continue and with another style of programming or definition. These x's are a bit, we can choose another style which is more sophisticated and easy or simple. Even either we provide these type variables as the argument, or replace them with space holder. In any case, we had to write something. We cannot just leave their spaces as empty, or otherwise it would give an error. So there is a directive called arguments that allows us to define implicit arguments. The implicit argument is the one that that is implicitly there but is not mentioned there. So using implicit arguments, we can define the same function in a much more sophisticated way, where we would not need to repeat these type variables or their space holders. So to use implicit arguments, we first need to define type variables in the constructor or in the function name as implicit. Or we can also define some arguments in the function type as the implicit. So for this purpose, normally for the constructors, implicit arguments can be explicitly first defined using the argument directive. So for example, argument null is null is a constructor, and with null we are using x as the implicit argument, which is enclosed in the curly braces. So for whenever a null is used, the implicit argument is the type variable x. Similarly, for the cons constructor, the implicit argument is that is the first argument is x, and it follows with two other arguments, and we can just replace them with space holder if we don't remember them, or if we don't want to name them. So what happens here? We know that there is a variable of type x, and there is a list of type list of x. Okay. Similarly, we can arguments. We can for the repeat, there is an implicit argument x, and x count. So these are the two arguments, and the first argument is the implicit. So after this treatment, we can define, for example, we can use them definition list 1 2 3. Let's suppose I want to define a list, and I want to define this with for cons 1, cons 2, cons 3, sorry, there is a parenthesis, cons 3, and null. So what I have done here is that I am skipping after cons. We should have a type variable x, but now I have mentioned that it is implicit, so I'm not mentioning that. For example, we should have a net data type here, but now I'm not mentioning that because I have told to the Coq compiler that whenever cons is used, there is an implicit data type as well. So even if I do not mention it, Coq should determine that from the values here, and should put that type up the value here, and that type should be put here, even though I'm not mentioning that, but Coq finds it out from these arguments. So I'm not mentioning the data type type variable x here or net here. So it's more it's a simple style of defining list. And for the functions, we can also define some of the arguments to be an implicit, and for that, to define an argument to be implicit, curly brackets are used. So let me use that style where the arguments in the function is declared to be implicit. Fix find, and we continue with the same repeat, and it is triple dash. Okay, so the argument that is to be defined, we plan to define the type variable to be the implicit, and it is encloses in the curly braces, and the rest of function goes as usual. X is a value of type x, and we have a count of type net, and it should return list of type x, and it is defined to be as match count with, if it is 0, then it should return null, and we are not mentioning any type here. Previously we had mentioned type x, or we had underscore here, but we are not mentioning anything. So there is a type variable missing, and that is implicitly passed here, and this implicit data type is taken as the type variable here. And if it is successor followed by something, then we should return cons x and repeat prime 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 x count prime, and it is ended with dot. Okay, so this function is more simpler than this style, and it is more simpler than this style. So so we improved the style of defining functions using polymorphic style. So we had x here, we replaced it with underscore, and we removed that. We skipped that. We skipped even that underscore by defining the data type variable to be as implicit. Okay, so we can define many other functions in this way, and we would continue in coming lecture by defining list in the same implicit style where we define list, but we mention the data type x here, and we would be able to declare this type variable to be implicit as well. So as we declared the argument of the function to be implicit, so quite that way we can define the argument in the data type to be implicit.